The scaling of artificial intelligence is currently constrained by the physical heat of the hardware, which has overtaken algorithmic complexity as the primary bottleneck. To reduce processing latency, the industry is physically packing logic layers closer together, shifting from flat processors to vertical compute cubes. But wrapping active processors in additional layers of silicon transforms the interior of these cubes into inescapable thermal traps. This creates a scenario known as dark silicon. To prevent a chip from melting itself under load, up to 40% of its volume must remain powered down and inactive at any given time. There is a direct contradiction between the massive energy densities required for continuous high-speed neural processing and this forced underutilization of the hardware. Extracting this trapped heat is the single mandatory physical prerequisite that must be solved before artificial intelligence can scale to superintelligence. Right now, the industry attempts to cool these 3D architectures using standard 2D cooling surfaces, like flat cold plates and heat sinks. This chart perfectly illustrates the geometric mismatch. Volumetric heat generation scales cubically, represented by the red curve. Meanwhile, extracting heat across a flat surface scales quadratically, the lower blue line. This mathematical divergence forces a hard limit. Trapped heat rapidly outpaces the hardware's ability to shed it. The solution proposed to bridge this gap is the infinite fractal descent, or IFD, manifold, a nonlinear 3D vascular cooling structure. Instead of placing a cold plate on the outside of the chip, the IFD weaves directly through it, matching volumetric heat generation with volumetric heat extraction. Standard flat physics can no longer dissipate the heat required for these calculations. Hardware architecture must physically descend into non-integer fractal dimensions. At the macro scale, the IFD manifold is constructed as a 10-level bifurcating network embedded completely inside the 3D logic stack. It operates as a directed acyclic graph, mimicking the highly efficient branching vascular networks that evolved to move fluids and gases in biological brains and lungs. This diagram displays the math dictating how channels split, Murray's law. The parent pipe's radius cubed equals exactly twice the daughter pipe's radius cubed. Preserving this ratio minimizes mechanical energy spent pumping fluid, multiplying downwards across 10 distinct levels of depth. At iteration depth 10, the manifold terminates into millions of microscopic capillaries directly at the transistor backplane. This specific fractal geometry yields an effective surface area 10,000 times larger than a standard flat cold plate. Applying Murray's law effectively takes the extreme high-density heat of a 3D cube and unfolds it across a massive, highly efficient internal boundary. Transitioning from the overarching network down into a single microscopic terminal capillary at level 10, we encounter a fluid dynamics problem. The coolant must move fast enough to actually pull heat away from the transistors, but if it moves too fast through these microchannels, the resulting friction causes a catastrophic pressure drop, stalling the entire system. The fractal geometry solves this through Reynolds number equilibrium. Because the fluid velocity drops exactly in proportion to the splits, the terminal velocity remains perfectly within the transitional flow regime, balancing speed and pressure. But this creates a secondary threat at the microscale, the thermal boundary layer. When fluid moves smoothly, a stubbornly stagnant film of water clings to the channel walls, acting as an insulator between the chip and moving coolant. To break this insulation, the terminal capillaries of the IFD are engineered with specific curvature and internal rifling. This specific internal structure forces the water into a spiraling lateral motion as it travels down the tube. This creates synergistic vortex induction. The rifling generates secondary flows that interact with Dean vortices, swirling patterns caused by the channel's recursive curves. Instead of sliding smoothly, the fluid stretches and folds, actively tearing away that stagnant, insulating boundary layer to expose the cold, moving water directly to the heated surface. By utilizing channel geometry to passively induce microturbulence, the manifold achieves a 340% surge in heat transfer efficiency. Below the fluid, there is one final atomic bottleneck to solve, the solid-state interface, where the silicon die physically meets the copper cooling manifold. Energy has to transfer across two entirely different materials with conflicting atomic lattice structures. As shown here, this mismatch causes capacitor resistance. At the microscopic level, these surfaces are jagged. When heat energy, carried by particles called phonons, hits this chaotic gap, it scatters instead of crossing over. Traditional thermal pastes and adhesives are used to fill these gaps, but they possess low thermal conductivity, effectively acting as secondary insulators. These rigid joints also undergo physical fatigue over time, slowly cracking as the copper and silicon expand and contract at completely different rates. The IFD bypasses this entirely using low-pressure nano-silver sintering. 20 nanometer silver particles are injected directly into the interface, flooding the jagged gaps and fusing the silicon and copper into a single block. This near-monolithic bond allows photons to travel directly through the joint, boosting thermal conductivity past 250 watts per meter Kelvin. Structurally, this silver layer remains mechanically flexible. It absorbs the thermal expansion stress between the two metals, reducing joint fatigue by 80%. Eliminating this atomic-level photon scattering ensures the macroscopic fractal network above it actually receives the full volume of heat it was engineered to extract. Executing this design poses a direct manufacturing question. How do you physically construct a microscopic 10-level branching network with internal rifling? The answer is advanced 3D printing. Specifically, selective laser melting fuses specialized copper alloys layer by layer, forming geometries impossible to cut with traditional machining. This process provides a synergistic benefit. The microscopic surface roughness left behind by the laser acts as an additional passive turbulator, enhancing the heat extraction of the fluid even further. These benchmarks show the final resulting metrics of the integrated system. The manifold achieves a total heat flux capacity exceeding 2.5 kilowatts per square centimeter, easily supporting dense logical arrays drawing well over 1,000 watts. Because of the mathematically precise branching, the pumping power required to push the fluid through the manifold drops by 40%. This yields a coefficient of performance exceeding 10,000. For every single watt of mechanical energy spent running the pump, 10,000 watts of heat are extracted. The IFD system provides the thermal headroom necessary for true 3D compute stacking, shifting cooling from a power-hungry constraint into a high-efficiency utility. When an integrated 3D compute cube operates with an IFD manifold, every logic layer can run at full capacity without triggering thermal throttling. By cascading these engineering solutions, the fractal macrogeometry, microvortices stripping boundary layers, and nano-sintered interfaces, the system maintains precise thermal control. This extreme uniformity eliminates hotspot timing jitter entirely, allowing perfectly synchronized processing across every stacked vertical layer simultaneously. The impenetrable thermal wall that previously forced the computing industry into utilizing dark silicon has now been completely dismantled. Hardware design is no longer limited to merely managing heat after it builds up. It proactively integrates thermal extraction into the architecture through geometric optimization. By entirely decoupling computational performance from these physical volume limits, we've removed the thermal barrier that previously dictated the ceiling of artificial intelligence.